We are delving into the world of chemical reactions. Two elements or more reacting. When elements react, when chemicals react, it always involves a transfer or a rearrangement of electrons. The center, the nucleus, doesn't do anything. The protons and the neutrons, they're there. They define what the atom is, but they don't interact. Most of the electrons are not involved in the reaction. Only the ones on the surface are going to interact. So for all of the electron configuration work that we've done in the past, the only ones we care about are the outermost electrons. So we have a special name for those, and that is valence electrons. So the valence electrons are the electrons in the outer shell or level. We use the word shell and level interchangeably. So if I have a lithium atom with its 3 protons, that's element number 3. And so I know it has 3 electrons. Now the first level only holds 2. All of the rest of the levels can hold more. So the first 2 electrons go in that level. The third one goes in the second level. So if a valence electron is electrons in the outer shell, the only valence electron for lithium is this one. And so we say lithium has 1 valence electron. Most of the time when we're talking about electrons, we're only going to talk about the valence electrons because the rest of them don't do anything. So now that we know that they're there, we can kind of ignore them. Now, if you have an electron configuration, remember that what we want to get from the electron configuration, you don't have to be able to write it on your own. Just know that this is the level, so the second level and the first level. And since we only care about the electrons in the highest level, we only care about this 1 electron. So we say it has 1 valence electron in the highest level. So you'll continue to see this notation. You don't have to write it, just be able to interpret it. So here we have a larger atom, fluorine. Now fluorine is element number 9. Its atomic number is 9, so it has 9 protons. It also has 9 electrons. And again, we see 2 electrons in the first level, 7 in the second level. Look at our configuration. The first level has 2. The second level, remember, is split between 2 sublevels. We don't draw the sublevels, but when you see this notation, you have to remember that second level, that's the same level. And so this is telling us there's 2 electrons plus 5, there's 7 electrons. When you see this notation, 7 electrons total, and we can draw it like that. Now what we want to do is be able to look at the periodic table and determine how many valence electrons an atom has. Now you'll notice here we have the periods, 1 through 7. And as I've said, we don't really use those too much. The group numbers go across the top. And I've mentioned before that we're going to use the 1 through 8. Well, we're going to use the 1 through 18. Just to avoid confusion, that's what your book uses. And so we'll go with this. So this is the group number. Now the nice thing about the group number is it tells you, or at least allows you to figure out, the number of valence electrons. Now that's pretty simple because if I have group 1, that means it has 1 valence electron. Now what we want to do is we want to draw a diagram of this. And so consider hydrogen. It's in group 1, and what someone came up with is this idea called electron dot diagrams. And quite simply, to represent an electron, you use a dot. So hydrogen, because it's in group 1, has 1 valence electron, and so we're going to put 1 dot. Now everything in group 1 also has 1 valence electron. So lithium right below hydrogen has a single dot. Sodium right below that has a single dot. All the way down. These are electron dot structures, also called Lewis dot structures, because they were named after Lewis. Now, just like group 1 has 1, and group 2 right here, all of these elements have 2 valence electrons in the highest shell, and so we can do dots just the same. Now, it doesn't matter too much where they go, but being as electrons repel each other, they want to be as far away from each other as possible, and normally you'll see it written like this, where they're on opposite sides of each other. So beryllium, 2 electrons because it's group 2. Magnesium right below that. Calcium, also group 2. And again, we've said this is important because this is why they behave alike. Now, all of these guys, remember these are transition metals, are group Bs, they're sometimes called. So we don't mess with these because they have all kinds of exceptions and don't always follow the rules. So as we're learning, we're just going to ignore those. Likewise, the inner transition, we're going to ignore those. So we're going to jump all the way over to here. Now, for these, in order to figure out the valence electrons, we are going to subtract 10. And so that's something you're going to have to memorize. And so where this is group 13, if we subtract 10, that means it has 3 valence electrons. And this has 4 and 5 and 6 and 7 and 8. So our group 13, I might call it group 3 because that's the old way of doing it. So group 13, these all have 3 valence electrons. So boron, again, I'll just put 3 dots. It doesn't really matter where, but we try to separate them out. So there's boron. Right below that is aluminum. And then we have gallium below that. And so again, group 13, or group 3, if you want to call it that, I'm fine with that, has 3 dots. Now group 4 has 4 as well, but we're going to save that. We're going to hit that later. So we're going to skip 4. And let's go to number 5. So group 5, well, the same idea. It's group number 15, but we're going to subtract 10. And so it has 5 valence electrons. So nitrogen, 5 valence electrons, we want to keep them far apart. But once we do 4, now we have to double up. And so we're just going to double up any of them. It does not matter where, as long as you have 5 dots. We'll try to keep it, well, we will keep it 2 maximum per side. All right, so phosphorus, group 15, subtract 10. I'm in group 5. So phosphorus, I'm going to go 1, 2, 3, 4. Let's put the 5th one over there. There's phosphorus. And let's see, group 16. Well, if we subtract 10, that means this group has 6 valence electrons. And so oxygen, we'll use oxygen a lot in this class. There's 1, 2, 3, 4. And now we double up. And again, it doesn't really matter where. There's 6. And we'll skip over to fluorine. We'll encounter fluorine a lot. Now we're in group 17, so it has 7 valence electrons. And so 1, 2, 3, 4, 5, 6, 7. And then lastly, all the way to group 18, they have 8 valence electrons. So I'm going to go with neon. And so 8, there's 1, 2, 3, and 4. Now I can double up 5, 6, 7, 8. Now, where this is going is that it was understood, or it was realized, that every atom wants 8 electrons in the outer shell. This is called the octet rule. Octet being 8, rule being rule. So all atoms, all elements want 8 electrons in their outside shell. Now there are exceptions. Remember we said helium only wants 2 because it's too small. Well, as does lithium and hydrogen. Those guys only want 2. They're not big enough to hold 8. But other than that, the octet rule says all atoms want 8. Now, one of the key things for this section, this chapter, is to memorize and remember that these are the metals, pretty much. And metals are going to get their octet. They're going to achieve stability by losing electrons. Whereas the nonmetals, those elements largely on the right, are going to gain electrons. So that is something you need to memorize. Metals on the left, they're going to lose. Nonmetals on the right, they're going to gain. This is the foundation for the whole chapter. Now you might be thinking, if these guys want to lose and these guys want to gain, maybe they should get together and come to some sort of arrangement. And that's what we'll get into next.